Electron affinity. If an electron is added to a neutral atom in its gaseous state and a stable anion is formed, energy is released. For example, when a bromine atom picks up an electron, it forms a stable bromide ion, Br. If 1 mole does that, the amount of energy released is equal to 325 kilojoules. So this is the equation here. This is a gaseous bromine atom, and it picks up an electron here, and you form an ion of bromine here, or bromine. We say bromine in Guyana, you say bromine here, plus that amount of energy. We say EA is equal to negative. Give negative because it's an exothermic reaction. You'll do this concept in grade 12 chemistry, where you do enthalpy changes. And if it is an exothermic reaction, it is given a negative sign. So that's the amount of energy that is released when 1 mole of bromine atoms pick up 1 mole of electrons. Okay? Now, I've written a lot of stuff here. The energy change that occurs when an electron is added to an atom in its gaseous state to form a negative is called electron affinity. This is sometimes called the first electron affinity. The more stable the negative ion that is formed, the more energy is liberated. The energy release is indicated by a negative number. Okay? The greater the negative number, the more stable is anion form. The closer an electron comes to the positive nucleus of a particular atom, it results in greater stability of the anion form and more energy is liberated. This, of course, depends on the unique electron configuration of the atom and its nuclear charge. So let us use this thing to depict how energy is released. Here we are having 2 charges. This is a positive charge and this is a negative charge. Emanating from these charges are what is called electric field lines. Every positive charge have electric field lines moving away from them, and the negative ones have the one coming into them. So when a positive charge is in the vicinity of a negative charge, these electric field lines will overlap here, they will link, and that will create an attractive force between these 2 charges here. Now, when these 2 charges come closer together, energy is released. In this case, we'll call this E1. Now, if we bring these charges a little bit closer together, you get a different amount of energy released, E2. And in this case, E2 will be greater than E1 because the charges here are coming closer and closer together. So the point to note is that the closer a positive charge comes to a negative charge, more energy is released. Okay? Now let's see what is happening here. In some atoms, the negative ion form is unstable and it spontaneously breaks apart to produce a neutral atom and an electron. So in some cases, if you add an electron to the atom, it will break apart spontaneously to release back the electron and produce a neutral atom. In these cases, to keep the ion intact, energy must be supplied, and this is indicated by a positive number. The greater the positive number, the more unstable is the anion formed. So if you put an electron to an atom, and an ion form is unstable, we need to use the energy there to keep that there. So the more energy you need to keep that electron is telling you the anion form is very unstable. Now there's something called second electron affinity. Our second electron affinity will have a positive number because adding another electron will experience more electron-electron repulsion from the already negative ion, making it more unstable and requiring more energy to keep it intact. In other words, let us say how that bromine atom picks up an electron and it forms a negative bromide ion. Because of that negative charge in the bromide ion, it's difficult to put another electron there because the bromide ion is negatively charged and it will repel that electron that we're trying to put on there. This here is a table of electron affinity. Here you can see all of these here, with the exception of group 2A elements, and group 8A elements, all of them have negative electron affinity except these that are positive ones here. And this one here, nitrogen here, is 0. So how do we explain this again? We'll use the same concept of atomic orbitals and the energy in these atomic orbitals to try to explain why you need energy to create these ions here, why you need to use energy, and why these ones here, of course, are liberating energy. And you can see a little trend here. See, we said that the closer the electron is to the nucleus, more energy is released. Look, potassium is bigger than sodium. That's why when an electron comes on, it only gives up that amount of energy. Sodium will give up a little bit more because that outer electron are closer to its nucleus. Lithium is here more, and of course hydrogen is there, okay? Now let's go and see how we can explain why these need energy to create an ion, and why these also need energy to create an ion here. We'll use magnesium to illustrate that for group 2 elements. Now look at this. This is the electron configuration for magnesium, okay? Magnesium has, how many? 12 electrons, and it's holding on to these nicely here. If I put one more electron there, see where that electron is going? That electron is going far away. It's going to a 3p subshell. And therefore, there's a tendency for the nucleus not to hold on to the electron because it's going farther away from its attractive force. And therefore, you need energy to keep that there. Similarly, same thing is happening here. Look, this one here is neon. Another electron added there will go there, and that's farther away from the nucleus, and therefore it needs energy to be added to that atom there. Energy is always going to be positive for these. No energy is released, nor energy is absorbed when you add an electron to nitrogen. So nitrogen is this, 7 electrons here. But the only plausible explanation that I can give is this. Because this one electron comes inside here, it causes more electron-electron repulsion here. But again, in nuclear charge, mitigates any electron-electron repulsion there. So it's that balancing off effect there. That could be a plausible explanation as to why, when you add an electron to the atom of nitrogen, there's 0 change in energy. So I hope you understand that, okay? And these here, of course, are some questions that I have. They're repeated in the solutions manual, and the answers to these are given too. So you can avail yourself of that book. So see you next time again. I hope you enjoy listening and you've learned.